Let me just give you a brief intro kind of into my intellectual background and journey towards AI safety. I was born an hour south of here, and I went to a local kind of French grammar school that didn't prove to be the ideal kind of match for me. It was a humanities school in French, and I didn't like French much, and I wasn't a fan of humanities. So after that, I went to University of Cambridge. I did math and physics for the first 3 years, and then I always had a really kind of keen eye on AI, but I thought it wasn't working all too well. Around the time, neural networks didn't seem, at least to me from my kind of distant vantage point, to do much of anything interesting. And I thought, out of all the functional approximators, why this in particular, right? It didn't seem obvious at all. It still doesn't seem obvious right now, but I know at least empirically they work. At the time, I didn't know they worked empirically, so I wasn't very convinced. But around the year 2015, AlphaGo managed to be the European champion in Go, and I thought, oh my god, this shouldn't have happened another 30 years. This shows there's magic happening there. And so I switched to AI, and I moved to California and started a master's program at Stanford. And I was kind of gradually transitioning from physics to AI around the time, mainly kind of by offering my services to physics labs and saying I can automate certain parts of your pipelines if you pay me for 3 months. And then so I did this for 4 or 5 stints, from astrophysics, X-ray detectors, all the way to quantum computing. And I kind of built up a kind of compendium of physics ML papers around the time. And after that, people finally were able to kind of pay me to do AI full time. I spent some time at Google Brain as an AI resident. It was a program that kind of allowed you to spend a year doing AI research, even as a non-AI PhD. Spent half a year at DeepMind as an intern, and then spent quite a lot of time at Anthropic, building up parts of Claude 1 and Claude 2. Then briefly, as Hansa mentioned, I was at Stability AI, leading the LLM team. Then many things happened, and I left, and so did many others. And I joined Google DeepMind a few months ago, so that's where I'm at right now. This talk will be primarily based on the papers whose archive links or archive numbers are shown on the slide. And the kind of the meat of the talk is the last bolded number. All right, so I call this adversarial robustness as a laboratory for AI alignment. And I think there's a compelling case to be made that solving adversarial brittleness and robustness is a necessary kind of pre-step for solving anything kind of more complex in the space of AI alignment. So I kind of focus on the technical aspects of this. Let me give you a kind of brief intro into the problem setup, right? So in image classification, you're trying to convey a human implicitly specified function that lives in your brains to a machine. And you would like the machines to do what a human does, right? So how do you do that? So normally when a human kind of looks at pictures, you can recognize the parrot, the tortoise, Prague, and you have some implicit function living in your brain that's kind of not explicitly accessible to you on the conscious level. You kind of look at things and you know what they are, right? So you couldn't sit down and write down the rules for saying why the parrot is a parrot, which pixels are causing the parrot picture to be a parrot. And then different humans have probably different functions that are kind of implicitly specified in their brains, but we kind of broadly agree on basically everything, apart from a few edge cases, like the blue and gold, black dress, and these optical illusions that show that there are points at which in the human functions kind of disagree with each other. But typically, they agree very broadly, even in kind of pretty attacked, kind of actively exploited regimes. And so the way we do this, we specify a data set. So we label images, and then we have a bunch of them, and we show them to the machine. And the machine uses some functional approximators and optimization, so neural nets in this particular case, and variants of SGD, gradient descent, to kind of get its own function G, mapping inputs to outputs. Now, the question is, they both work really well at recognizing things. They both match each other in many of the desired properties. And the question is, are they the same? This has an analog in AI alignment where you're trying to convey some values or some behaviors to a machine, let's say by providing a huge corpus of text, fine-tuning on instruction following or whatever. And then the machine develops its own version of the function you implicitly have in your head for what the desired behavior should be. And now the question is how do we distinguish, or how do we recognize if they're the same, and how to probe the differences between them. So image models are extremely robust. That's an interesting aspect of this. They're extremely robust on average, and they get more robust with scale. So that's another kind of like beneficial side product of making networks bigger and making data sets bigger and increasing the number of flops we invest in things. So, we have a data set, they're classifying things into classes. It could be not just classes, but like, let's say textual descriptions of the images, so it doesn't have to be this kind of like poor regime, but I'll stick with classification kind of like as a toy example here. And these classifiers, they are able to recognize the thing under a variety of noises. They can be, Gaussian noise, they can be blurs, they can be pixelations, like different attacks in the average case. These models have no trouble recognizing the underlying bird. And so we can actually quantify this, and there are data sets that are kind of standardized where we increase the strength of these attacks and we measure how the model kind of loses its recognition capacity as we increase the strength of kind of this like a random noise being added. And these models are extremely robust. I think I haven't seen kind of like a definitive answer, but they seem as robust as a human in recognizing images under these kind of like random, untargeted noises. So this is kind of like the tier 1 of robustness. You would like the thing to kind of like still work even if you add kind of random pixels. You wouldn't like the thing to be brittle if you just change one pixel by like 1 out of 255 values, right? So the models are by default extremely robust in this way. They're also really good at auto-distribution detection, which used to be a really kind of unsolved issue for a long time in machine learning until a few years ago. And so here I'm kind of discussing a result we show in a paper called Exploring the Limits of Auto-Distribution Detection that I co-wrote with GRN and Balaji Lakshminarayanan, who are my colleagues right now at DeepMind. And essentially, we basically show that if you make models bigger, the kind of embeddings they produce are extremely good at distinguishing even very nearby images or nearby data sets. So let me tell you what I mean. The general setup of this kind of like second tier robustness is roughly this. You've got an in-distribution data set, which are images that you train on. And there are a data set of certain classes, let's say buses or whatever. It could be CFAR10, and that's your in-distribution training set. And then you've got another data set that's called the out-distribution. And at test time, you would like to distinguish images drawn from either of the data sets, their test sets. And so this used to be a pretty big problem. In the simpler cases where the images are kind of distinguishable based on surface statistics, like here, between the images of planes and animals and cars and numbers on the right-hand side, that's a very easy task. That didn't used to be a big problem at all. Because you could look at, let's say, the two-dimensional Fourier transform spectrum of these images, and you could easily distinguish whether it came from the numbers data set or the CFAR 100 data set on the left-hand side. So this wasn't the problem. The problem was when the images kind of on the surface look the same. So let's say CFAR 100 and CFAR 10, very famous data sets, that kind of like broadly look roughly the same. You kind of have to like look deeply into what's in the images to be able to distinguish them. And that's called near OOD because the data sets are near. And this used to be an unsolved problem to a large part until a few years ago. And there were kind of two broad approaches that people like deployed to solve this. One, the most prominent until recently, was kind of the mathy approach. You kind of had your in-distribution data set, and then you wrote like 100 pages of math in your appendix to try to like make the classifier behave well outside of the support of the training set. And so that math was supposed to kind of carry you over from the in-distribution training set to the OOD regime and make the model kind of like behave like in a sane, like well-behaved manner. This proved to be slightly beneficial, but given the amount of effort and math kind of involved in it, the returns kind of like petered out after a while, and the progress was pretty slow. The second approach that I favor, that I think is kind of like broadly applicable and now kind of is more prominent due to scaling and kind of data and flops playing a bigger role in kind of getting intelligence out of machines, is kind of having a massive implicit pre-training data set out of which you carve out the in-distribution data set, and that broadly contains even all the out-distribution things as well. And so it's an alternative, simpler approach that proved to work better in the end, just having a massive pre-training and having the pre-trained model understand the world kind of in general, and then using that for detecting things. So this is a particular task. Roughly 50% is like chance, 100% is like being able to distinguish them perfectly. And so the previous best models before this paper, using kind of a lot of math and a lot of theory, were kind of like at 85.6. And human performance was way above, like the 95.9 is a score humans have. The fun part is that I am the human actually that benchmarked this data set, because when I came to the problem, there was no number for a human, so I kind of didn't know what the maximum is. So I spent 20 hours or so just clicking on images and trying to like distinguish the two data sets. Yeah, so you know, the number is for me, yes? Oh yeah, by the way, if you have like short questions, just ask away. Longer questions we can answer at the end, because I think this will not cover the full hour. Yes?
Yes, why is distinguishing between two data sets a more valuable, interesting approach than just actually labeling the pictures themselves?
Yes, so it's not more interesting. It's like a second tier of robustness in a way that if you had a classifier that was not robust for kind of OOD behavior, it would see a picture it has never seen ever. Let's say you trained on CFAR 10, and then you try to use it for like dermatology, like cancer detection. And the model would look at like a skin lesion and it would say 100% this is a car, right? Like you would like to control the behavior of the model, and you would like the model to kind of be able to express I don't know. So this is like the version of that. This robustness is kind of like a covert expression of like uncertainty in the model. So this task is trying to like make sure the model doesn't like overclaim on data it hasn't been trained on. Yes?
Are you doing a separate training procedure for the out of distribution detection, or you're just reading it off the logics of the model?
Just reading it off. So like I couldn't train, you know, like that would be kind of like cheating. You would be, so this is like the only thing it sees during training is the in distribution. It never sees any out distribution images at all in a way that it would like end up changing the weights of the model. So it's like it has to be kind of separate. Otherwise, like it's like easy as a task. So I would like the model to be robust against unseen things.
And is that just like you set some threshold of like if you're below this percent?
Essentially, but you kind of like fit like you know, Gaussians to like clouds of the embeddings, and it's called like Mahalanobis distance, but it's like literally just a number of sigmas you're away from a Gaussian fit to the embeddings. But it turns out if the embeddings come from a good model, from a big model, this is sufficient at like doing this. Yes?
I think you just answered my question for that.
Okay, cool. Yeah, so you know the human performance was well above the previous models, and it took like the progress was like 1 percentage point a year, so very slow progress. Sorry, go ahead.
So I guess so the goal was to like the classifier to say like, oh, this was from image set CFAR 100.
Yes.
10, right? So like, what is the difference between CFAR 100 and 10? Because they kind of look the same.
Yeah, that's the thing. They kind of look the same, but like the semantic content is different. Like, you know, there's like a car in one and there's a truck in the other. There's like a tank in one and like a tractor in the other.
Oh, it's like very manual. It's not even like this is a set of things. It's just like, oh, like this.
No, it's like it's very manual. It's very manual. So it's actually a pretty challenging task even for a human.
So when you did you just like memorize like which was in which set?
I memorized which classes are in which set, and I was like looking at it. I made it like a bit harder for myself because I didn't see the example images of one. I just knew like a tank is in CFAR 100, but it isn't in CFAR 10. And like a car is like in CFAR 10, but not in CFAR 100. So it was like a pretty tedious manual task. Yeah, so I labeled for like 20 hours, and I got a number. And I had other people labeling as well, so like to verify kind of consistency. And yeah, so basically by taking a large model, we were able to close the gap. And there was like no math involved. The paper is extremely simple. The trick is literally using a large model. The large model is more robust in this kind of like being able to say, I don't know regime. So that's another kind of nice point of evidence that like these things are actually very robust. And we used bigger models still, like it outperformed humans slightly, and then we ensembled them eventually, and they were like even better. But basically, they did manage to close the gap to the human performance. And the gap between 100% and the human performance, when you analyze the mistakes, quote unquote, in these models, is due to mistakes in the data sets themselves. There's like mislabeled images in the data set. So like, I actually like, we were leading the leaderboards on papers with code in this task, and then like a paper came and said they got like 100%. And like, this is like literally impossible to get 100% on, because there's mistakes in the data set. And so if you kind of like go by the ground truth of the data set, you always, even if your model is like actually superhuman and like never makes a mistake actually, it would be labeled as a mistake based on the ground truth that's like wrong sometimes, like very rarely. But there's a fox labeled as a deer and a kangaroo labeled as a deer, you know, mistakes like that. The TLDR is that we basically saw that big models are robust not only against noise and these kind of like untargeted things, they're also robust in the sense that they do not overclaim out of distribution. They're able to distinguish very nearby data sets very well. And scale actually did help a lot. We saw a really nice empirical kind of like scaling law, but not really a law, you know, in the physics sense. But the better the performance was on the like classification task, the better the performance was kind of linearly on this like being a robust task, you know, being able to say, I don't know, task. So that was really nice. So yet, yes?
What is the actual pre-training data set that you're using for these?
Yeah, so are you asking like if it contains the auto-distribution data set?
Well, I guess that would be a worry, but also even beyond that, it's like what is it being trained on?
Yeah, so this gets me to the weeds of this thing. So I had a large argument with one professor at Oxford when I kind of produced this result, because the kind of like the letter of the task is you should not like in any way kind of expose the model to the things that like the OOD data set includes. But practically, the spirit of the task is to make the model robust against the, you know, unseen examples. And so the model, the pre-training data set doesn't literally include the data sets we're dealing with in the OOD setup, but it does include like images that like contain the same concepts. So like there's like tags and, you know, everything that we as classes we're trying to like see either in the in or out distribution data set is contained as like semantic classes in the pre-training data sets. So likely the thing kind of leading to this high performance is the model being able to trigger the like underlying existing features that it learned about in the pre-training. So I think that's maybe answering what you were asking.
Yeah, I guess so. So then it might, this kind of technique might not be useful in certain domains, like, I don't know, in cancer detection.
Yes, yes. So cancer detection, probably yes, but I actually will show when it breaks in the next few slides. So yeah, this is good, but like it also has like pretty significant limits. Okay, thank you for the question. So, you know, the punchline is that like, yet the classifiers I talked about, the image models I talked about, are actually broken really easily. Not by kind of untargeted noise or untargeted changes, but by motivated attackers. So these things are called adversarial examples, and they've been known since 2014. The paper that kind of coined the concept was this Explaining and Harnessing Adversarial Examples paper by Ian Goodfellow, don't know the middle author, and Christian Segedy, who's at X.AI right now and worked on math and reasoning at Google Brain before. So like pretty famous authors now. And essentially you can take a picture of a panda that looks like a panda to the model, like with a high confidence, and add this like very weak but very targeted noise to the image. There's a super stimulus to the network, and then it'll convince it really strongly that this is in this particular case, a gibbon. But it doesn't have to be an animal. It could be a tank, it could be a car, it could be literally whatever. And the result of such a perturbation will be the most gibbonous gibbon in the world to the model. It's not even like vaguely having gibbon-like features. It's like an extremely, the most convincing gibbon you can ever present to the model. Yes?
Couple of questions. First of all, the nematode there is not reverse engineered. Is this generated by the network running in the reverse, or is that just noise that then goes classified?
Yeah. Yeah, that's a good question. Like, how do you get this perturbation, right? Like, you could probably, there are like a number of techniques of different strength. You can have different levels of access to the model. It could be black box, so you don't really see the gradients or the insides of the model. It could be white box, which is the easiest. So if it's white box, I give you the model, and you can literally backpropagate through the model, and you can say, given this image I have, if I want to increase the probability of class given, how do I kind of infinitesimally change the pixels of the image? And you kind of repeat this process for a few hundred steps, and you end up with this targeted noise. So if you have kind of gradient access to the model, you can backpropagate through the model, kind of, as you said, kind of go back, reverse it, and then modify the image accordingly. There are other techniques that like do not need this like super privileged level of access. They're also pretty powerful. But there's a whole slew of kind of techniques, but yeah.
How does this addition work so you don't oversaturate like perfectly white pixels?
If you were able to like modify the perfectly white pixels?
No, if I would do a simple addition of two images and I have 1 or 2.55 pixel on the one side, then it will be a 1 or 2.55.
You have to clip it, yeah. I mean, what is the question?
If I have a white pixel on both images, do I just get a white pixel on the other image?
Yeah. I mean, this is like not, you know, but the thing is these methods are, the brittleness is so redundant that you don't really care that you oversaturate certain pixels. It doesn't have to be like exactly this. I'll actually like make this point more mathematically later, but it's like 10 to the 100 potential images you can like attack with, and you don't really care about, I could like black out like 90% of the image and not change it at all, and yet it would still work. Like it's extremely redundant. Yeah.
And last question, what's the epsilon before the sign?
Very small, like 0.007 here in this particular case. Anyway, so this is a really great example that despite the robustness on average, the robustness against a motivated, exploitative attacker is a very different question. Like you could have models that are like extremely not brittle, extremely robust, and yet they crumble you know, under very weak attacks, right? And so here's just like two more examples that I ran this morning. You know, a ship, I trained a model on CFAR10, 99.6 ship. You add this like extremely like weak rainbowish pattern, and now it's like 99.6 car. And the dog into a car as well. So it doesn't have to be a machine to a machine. It's like literally anything to anything. And this is an extremely surprising thing. And so also like on the meta level, people being surprised by this and not being able to anticipate this ahead of time gives me a kind of, it really like makes me doubt the value of armchair thinking about AGI alignment. Because if we couldn't even foresee this, which is a very simple, trivial case of kind of a catastrophic failure and brittleness by reasoning about these models, what is the chance we can kind of like foresee like way more complex, way less well-specified things? So this also to me is a motivating thing for like practical, empirical, technical AI safety or alignment work that has a very tight feedback loop with reality rather than like sitting in an armchair and kind of like thinking mathematical and philosophical thoughts just on the meta level. Yes?
You mentioned transferable here.
Yeah.
Is this talking about like you take the same pattern of noise and it turns ships into cars, it also turns dogs into cars? Or is it talking about the same pattern of noise between different networks?
Great question. I'll show you that it works this way as well. But what I mean here is like if you take the final like 99.6 car, like the ship that looks like a car, that'll be seen as a car by a lot of networks that are like independently initialized, independently trained, and often even trained on different data sets. So there's a huge amount of transfer between architectures, certainly between like initializations of the same architecture. And so these attacks are not spurious sometimes. They're not spurious kind of like peculiarities of a particular model and particular initialization. They're like broad feature-like behaviors that are shared between networks. So that's like the damaging thing. So that's why the practical worry is that someone will craft this kind of adversarial sticker, put it on a stop sign, and then a self-driving car that was like trained, you know, in a way that you don't foresee, you don't see the data set, you don't see the network exactly, will also be confused about what it's looking at. Like it might not see a stop sign, it might be designed to look like maximum speed 130 kilometers per hour rather than a stop sign. And the transfer from like your model at home to the model in the car, despite not knowing the details of the car, is the dangerous part of this practically. Yes?
So I heard this example with the stop sign several times, and it all seemed like a practical example. But I mean, I don't think it's like exactly fair, because if you, for example, just took you know, like a complete limited speed sticker and put it over the stop sign, that would also fool humans as well. This is like obviously, well, that's obviously illegal and everyone sees it, right?
Yeah.
So what we need is not, in this case, what we just need is to recognize the sticker as this kind of illegal as well. So it's...
I agree.
It may be like
That's the thing, right?
Because with technology we haven't deployed it, but like I think in the case of the stop signs, it's not the real danger.
I agree. This is like a pretty like contrived example, but if the detector is not a human, and if it's another machine, like it might not see the adversarial attack, right?
Right.
It'll,
You might need to have a human with a special camera.
Sure. Like, yeah, so the core thing here is the misalignment between the human representation, the function, and the machine function. So if the human is involved, for sure, I can see that there's like a weird rainbow sticker on the stop sign. Like, I don't know whether it's like a concert ad or like whether it's an attack, but I can be at least flagging it, you know. Good question, thanks. Right. So the thing is, these attacks are a bit, okay, yeah.
Is always full random noise necessary, or is this picture dependent? So for example, if I only do the sky with the ship picture, is it a car? And
Yeah.
if I do the dog face with the...
You can localize it if you want. Like, it's very flexible, yeah.
The localization is initial picture dependent, or can I...
Yes. It's dependent on the initial picture. Not always. You can make it also transfer in between images as well. The thing is, these things are also present in like the largest models we have, the $100 million kind of like massive runs. I don't have an example of that run here, but I wrote 2 blog posts when the OpenAI clip model came out, which is a model that has an image encoder spitting out a vector for an image and a text encoder spitting out a vector for text, and then you can compare the 2 vectors using cosine similarity, and its cosine similarity is the similarity between the semantic content of the text and the image. So you can say, I encode, you know, a picture of a cat using the text encoder, get a vector 1, encode a picture of a cat using the image encoder, I get another vector, and then, you know, this also gives me a vector. If they're close in cosine, the image contains a cat. Otherwise, it doesn't. So that's how clip works. And I just got a new MacBook, and I thought, okay, I want to like take it for a spin. So I wrote these like 2 blog posts that are extremely kind of like short, but they show that even these clip models have an extreme amount of brittleness in them, and in some sense they're actually easier to break using these adversarial attacks than the previous classifiers. I've got some examples here. There was a fun thing that you might remember about these models. So if you showed a picture of a dog, it sees a dog correctly. If you put a sticker over the picture of a dog, it actually sees a bird. So people kind of call these like adversarial examples in the paper. But I actually found that you can then add a pixel noise on top of the dog with the label bird on it, and it turns the whole thing into a frog as well. So you can kind of like, you know, despite the thing actually like looking like a dog, having a label bird on it, it's actually seen as a frog by the clip model. And so it just shows the amount of power you have in these pixel modifications as compared to the semantic content of the picture or the text in it. So basically you don't see a difference between the, you know, the final dog and the middle dog, right? Like in terms of the pixels. And yet it's like super convincing to clip. And the bottom example, like it turns a truck into a horse using the sticker. It still sees a bit of a truck in it, but mainly a horse. And by adding pixels that like confuse it, on top, it's a dog, according to the classifier. So I just like want to show you that even the biggest image models that we have are brittle against a motivated attacker. Yes?
Yeah, the serial noise is added on top of bird and the
Yeah,
dog.
yeah.
Have you done any examples of trying to do it only on the dog
Yes.
and have the bird on top?
Yes.
What did you find?
So you can overpower the label bird. So you don't have to like overlay the attack on the like text bird. It's like it still works. So you could do it in that order as well. Like the pixels are always kind of stronger in like convincing the thing than the label itself or the image itself.
Wow, okay, but I guess that's because you are really maximizing for the probability.
Yeah. It's very targeted. Yeah. Yeah, no worries. So I encourage you to read the blog posts. They're very short. And there's a code so you can rerun the experiments as well in a collab. And even kind of these like powerful like near auto distribution detectors that I showed you before, the models are really resistant to like not overclaiming or not being like over certain outside of the distribution. They still have these like amazingly easy to find vulnerabilities, right? So I wrote another paper called Adversarial Vulnerability of Powerful Near Auto Distribution Detectors. So I mean, the title says it all. But you can take a picture of a plane that's in distribution and add a little bit of noise on top, and suddenly this like extremely non-brittle, extremely robust, uncertainty-aware model thinks it's like the most like odd distribution image ever. Like you can shift it from one distribution to another. The decision can be like moved really easily from one to another with a very simple but targeted amount of noise. So I can take a crab here and just add this noise, and suddenly it's in the other distribution according to the model. And so this was unexpected, because I thought, well, this is great. We're getting like this amazing amount of robustness out of these models just by like having a massive pre-trained model. And yet, like I can, if I actually get gradient access to the model, I get white box access to the model, I can just like mess up the whole thing completely, despite its previous robustness. So it's like a bit of a conundrum, right? Like what's going on here? And we actually found that like stronger models, such as CLIP, fail faster in terms of the strength of the attack than the weak models. So there's an anti-scaling behavior where they get better with scale in terms of the average case robustness, but they get worse against kind of targeted attacks. And so what is the reason? I think the reason is the sheer kind of richness of the input space partitioning, the way you kind of carve out the space of all potential images into the semantic classes. And I wrote a short paper kind of exploring this right here, and someone asked a question that's actually very relevant here. So someone here, I forgot who exactly, asked if you can kind of like use the same attack on multiple images. You can, if you want to convert, people knew this for a long time, you can take one attack and convert a bunch of images into, let's say, a dog. Like, it'll always make that image into a dog. But it turns out, and this is a kind of short summer project, that you can take n images on the input of different things and give me n target classes. Let's say you want the first one to be a coffee pot, the second one to be an aircraft carrier, the third one to be a steel drum, whatever. So you give this to me, and I can design a single attack that, when added to each of the images, does the conversion to exactly the class you wanted. So I can pack like multiple attacks into the same perturbation, and they act differently based on the class, based on the image they're added to. So this is like a thing I wasn't expecting to work, and I actually like made it work by accidentally not doing batching correctly in my code and using the same attack for like multiple images. I was just trying to speed it up by having like a batched attack, but the batch dimension I forgot to set to like n. I kept it at 1 instead, and it still worked, and I was very surprised, why the attack is always the same. But it turns out you can do this easily.
How many?
So how many is a good question. Depends on the resolution, but for 32 by 32 by 3, the standard like low resolution CFAR 10 images, you can do up to like 100 or like 200 images. So like a significant number at the same time, surprisingly many, right? And so that means you got like an enormous control over the model here. And the flip side of this is that there's an enormous amount of richness in this space you're kind of exploiting. I want to showcase the richness here in a fun way, right? I started an image here. It's a plane. And I used one perturbation as a direction in like the space of pixels. Like it's like I'm moving. It's like one perturbation I'm adding to the image as a linear combination. I designed another one that like is an orthogonal perturbation to that, and I can, in the classes that like are the results of this classification, I can kind of trace images and numbers and letters and whatever I want. So this is like you take a space of like all images. And each point is labeled as a class by the classifier. So I can find a cut through that space that spells whatever I want, that like looks whatever I want, as I wish. Just showing that like even with these two perturbations, there was like enough richness in there that I could like trace whatever I wanted. So I drew a turtle in AGI because I have a tortoise at home, and AGI is an interesting thing. So like, but normally if you do this, like it might be a blob, of one class and like another blob of another class, or just like nothing. But I can design it in such a way that like it spells whatever I want. And I do this by just saying, okay, at like this point here, I'm forcing the class to be Daisy here at this like combination of like 10 times this image and like whatever 5 times that image. Like it has to be a turtle and whatever. And I optimize jointly to get these two perturbations on the x and y axes, and then I can spell whatever I want. So it shows an incredible amount of richness in that space, right? So exactly how much richness there is, well, I try to quantify it. And imagine a space kind of divided into cells. And the space is the space of all images. And the cells are the regions that are labeled as like cat and car and whatever. I've got n blue images. And using the same shift, which is the same perturbation, I want to convert the image 1 into like a blue class and the image 3 into like a green class. To be able to do this simultaneously, the number of images surrounding each of the blue images to have sufficient redundancy to be able to do this with like probability approximately 1, I need roughly, e to the number of images I can do it simultaneously 2 times the log of the classes. The log of the classes for like CFAR10 is like whatever, 2 or 3 or whatever. And the maximum is like 100. I measured empirically, which means that in this like simple toy model, I would have around 10 to the 100, roughly, neighboring cells around each image that are labeled, as like different classes. So that there's a lot of richness, right? And in particular, one really popular defense against adversarial attacks is just taking an image, attacking it, getting a bunch of samples around it that are misclassified, and then throwing them back to the training set and labeling them correctly and repeating this. This is called adversarial training. But imagine doing this for like 10 to the 100 like cells around each image, right? Like you couldn't ever exhaust this at all. So like that kind of shows the fundamental limits of that strategy if you're trying to exhaustively patch the kind of like misclassified like holes, quote unquote, around each thing. So this to me was like pretty surprisingly like rich. And I think it's like a nice like quantified number that you could like kind of like look at and say, okay, like the space is like obviously like really crazy. Okay, so I mean, to me, like this is like a vague collection, but I thought I'll mention it, right? Like high-dimensional geometry is like a passion of mine. I do enjoy thinking about it, and like it was a big part of my PhD. But just like one interesting example showing how weird high-dimensional spaces are is this: you take a square and you divide it into like cells, like 2 per dimension. So you've got like 4 squares here, and you put a circle kind of filling each there. And then you've got like a gap in the middle for the pink circle right here, right? It turns out if you kind of increase the dimension of this, the dimensionality of the situation, and you do the same for a cube, and then like you do 4-dimensional cubes and whatever, it's very easy to generalize. It turns out if you're at a dimension 9 and above, the middle sphere that's constrained by the spheres in the little cells around it actually spills out of the cube itself. And this is an insane kind of, to me, observation that like showcases how incredibly hard it is to constrain the behavior of high-dimensional objects using kind of enumeration of constraints. This was my first and only time I got a thing trending on Hacker News, because I think this is like a kind of like a nerd snipe. It's like easy to understand, but also weird. And I just drew it on my iPad, so like you see the quality of the visualization. But it turns out, that middle sphere spills out in dimension 9 and above. Sorry, I guess 9 strictly, just above strictly. Yeah, so it's just like there's a lot of like weirdness going on in high-dimensional geometry that likely is a part of the story. I don't know what part of the story it is like 100% yet, but I just want to show you that these things like do behave in like a weird manner. Okay, let me just move to the last section of this thing. I was like ramping up towards attacking LLMs as the main topic. But I think this was a good preparation, like setting the scene for it. So I wanted to understand, yes?
Like, to what extent is adversarial vulnerability surprising in retrospect? And like, to what extent does it seem solvable for image classifiers, or is it like plausibly just not possible to solve this problem?
I have a new paper coming out next week that kind of makes a headway in this direction, but I cannot speak about it yet. But I think in retrospect, it's like possibly, I can convince myself it's like not surprising in retrospect, but also it's very surprising. So I'm like very uncertain, even retrospectively, which way like my surprisal would go. Yeah, so sorry for not answering concretely, but yeah. So yes.
So I know that humans are also prone to illusions and kind of that stuff, but still it seems that humans are quite more robust than these models.
I agree.
Do you have any idea why that might be the case?
I have a paper next week on this. Sorry. So attacking LLMs, right? I want to understand how adversarial attacks happen and what properties of the situation are kind of causing them to be a possibility. And so I went to language models and I wrote this paper called Scaling Laws for Adversarial Attacks on Language Model Activations just last December. And I recommend you read it. I really like it. I think it's a cool paper. But reviewers disagree with me sometimes. So like I have a hard time getting into conferences. But I encourage you to read it anyway. So the general setup for an LLM is this. You've got input tokens. It's a sequence of discrete words, subword things or multi-word things. But you can discretize the input text into tokens. Each token gets embedded into a high-dimensional vector like this that I call an activation. People often call it a residual stream. I think it's just like a cultural difference in whether you came from like the mechanistic interpretability path like in the last few years or whether you kind of worked with other models before. But it's activation, so each word is a high-dimensional vector in the first layer, and then the LLM kind of like does a multitude of like passes on these vectors. At each layer, there is like 4 high-dimensional vectors still involved, but they're kind of mixing each other kind of in like an interesting manner such that in the end, they project back to the space of tokens and you get probabilities for the next follow-up token. So here, the sentence a turtle is A, and the model predicts the word species as the highest probability, next token continuation here. So the way I kind of like frame the attack is this. So you kind of sample from it. So like there could be randomness involved, but let's say you're deterministic here. You just go for argmax of the probabilities. Here, I frame this attack as allowing the attacker to add a perturbation vector to the first A tokens of the sequence. So I allow the attacker to design the epsilon0 and epsilon1, which are each a high-dimensional vector. And the goal for the attacker is to change the probabilities that are the result of this and to predict a particular word that I gave the attacker to kind of like influence the model towards. So let's say here it would be friend. Instead of a species, it would say a friend. It could also be a multi-target kind of continuation that I'm forcing the attacker to predict just by feeding the argmax token in the one pass back to the input context and then just like forcing the attacker to design an attack that, let's say, with 2 tokens of freedom on the input wants to predict 3 specific tokens as a continuation of that thing. So this is roughly the setup. You can view this as a classification task. You can view this as a classification task from the input activations, kind of being like the image here, to the v to the t, where v is the vocabulary size of the model, to the number of target tokens you're trying to force the model to predict, as the number of classes in this particular thing. So, I'm asking like, I give you a series of vectors that could be viewed as like pixels in the previous thing, and I'm asking what is a t token continuation of that? And there's like v to the t of them. So you're like classifying that sequence of vectors into one of the v to the t classes. This is great because here I have control over the dimensionality of the input, which is the number of tokens I allow the attacker to play with, and also the dimensionality of the output, which is the number of tokens I force the attacker to predict. Right? So unlike in the classification settings in Vision, where the number of classes was fixed to like 10 for CFAR 10, 100 for CFAR 100, or 1,000 for ImageNet, 21K for ImageNet 21K, very like substantial numbers, but still extremely limited. Here, the V is at least 50,000, and I can choose a T as I wish. I can like force the model to predict like 100 tokens into the future by crafting the right attack. And the dimension of the number of classes in that kind of setup would be 50,000 to 100. So like a very large number. Yes?
Do we need white box access to the model for that? And is there some sort of black box?
Yes. Yeah. Both. I'm comparing both actually at the end, and they're very similar in some sense. Thank you. Great question. Here it's a white box version of the attack. And so, you could also view this as like a resource lens on the problem where you've got some resources available to the attacker, which are the bits to play with on the input, the floats to play with on the input. And also, there's like some bits they're trying to fix on the output, like trying to dictate on the output, right? So like you could like view this as a resource thing as well. You could compute the dimension of the input and the dimension of the output and see whether there's like some relationship between them. And my hypothesis was that, this is like obviously true to me, that you need more dimensions controlled by the attacker than the number of dimensions you're trying to influence on the output to be able to like get from any point to any point. Just in terms of like the simple like mathematics of it, like if I control like one number on the input, I couldn't like move on like a two-dimensional surface on the output as I wished, right? Like I couldn't control that. So like the number of input dimensions to me has to be higher than the number of output dimensions for adversarial attacks in general from all to exist. And right, so is this practical? Well, like if you kind of have to like touch the activations, like normally you like have an API access to the model, so you don't really touch the activations directly. But there's two very particular and prominent examples where you do essentially touch the activations directly. For retrieval models, for example, the retro paper from DeepMind from few years back, the retrieved documents don't get added as tokens to the context. They get added as encoded activations directly among the activations of the encoded context. So there you are like having access to the activations directly. And also for every multimodal LLM, vision, audio, whatever, the multimodal input is added as activations directly to the model. So through that, you put like a side channel to the model's activations directly. You don't have to go through tokens. Like the images don't become tokens and don't get added to the context. They get like added as activations directly via the vision encoder. So this is also pretty practical. So let me show you what I can do, right? So the original LM, here you would have a simple like sentence, a simple math problem. That's the actual like input. 1 + 2 = and the model predicts 3 correctly. So that's good. Now I can take a random 25 numbers of the token 0 activation, and I modify them as such. Like these are the actual like modifications I made to that activation, and the model in the end says turtle. So like just to tell you what I was doing, the A at the beginning gets transferred into a vector. The vector has 1024 dimensions, I think. And out of those, I only take a random 25. And I don't touch other things, and I can move them such that the model in the end says turtle instead of 3. And also, if I get access to the full 1024 numbers of the first token, I can make it recite a poem after as a continuation. So this is the task I'm looking at here is extremely kind of like hard and unrealistically specific. I want the model to kind of like predict exactly the token IDs I'm asking it to predict. Like I don't want the mood of the answer to change. I don't want the like the negativity or the safety of the answer to change. Those are very broad, kind of high-dimensional targets. I want a specific sequence of like token 1123, token like 50, 50, whatever. I want exactly that. So it's a very like narrow target, and yet I'm able to like determine exactly the outputs of the model. Yes?
If the attacks like use the continuous embeddings, do you know if you quantize the models,
yes,
they suffer from the same, like, are they like still that vulnerable?
Yes, they do. The quantized models also do suffer. It's harder to design them, and they're like less susceptible, but they're still very susceptible. So yeah. All right. Yes.
For the previous slide, you said, like, is this practical? And you gave 2 examples. I wonder, have you done the experiments to, like, go from, like, right, this is just patching the activation directly. Yeah. Can you combine this with, like, adversarial image attack to...
You can. I tried, like, baby versions of that. But if anyone here is interested in, like, collaborating on this, I'm, like, very keen to try this. And I think it's very easy to try. But I think it's also, like, an impactful thing to try. So, yeah. Yes?
Is this a poem that the model's like already seen before? Like you only have to steer it in the direction of please regurgitate this poem by this author? Or is this like some custom poem it's never seen before that you're like steering it specifically to say, can you like make it generate any arbitrary text, a poem that you've created?
Yes, yes. So actually, all the experiments I do in the paper are literal random sequences like uniformly sampled from the vocab. So they're like not even like, like training set subsets or whatever. They're like literally like whatever, np.random.choice, like, range v, and like the length of the sequence I want. They're literally uniformly drawn from the uniformly drawn sequences. So they're the hardest targets one can imagine. This poem, it has seen probably. It's like a famous line from a famous poem. It's kind of like a motivating, like anti-death rant. I like that. But yeah, it works exactly as well for random sequences. It would be like less kind of visibly interesting if I just showed it like it says like white space dot whatever Korean character, Arabic character. But yeah, it works exactly. Yes, I think I'll have to move on.
Is this position sensitive, or does it look for 1 plus 2 equals or some other target token to start this rand?
It predicts a full rand. Like it's like not starting with like I'm not like saying O and then let it continue. I'm like forcing it to predict all of them.
No, I'm asking, is it waiting for, I think, 20 or so tokens to start the rand?
Yes. Oh yeah, I can separate the attack from the target by like 1,000 tokens, and it doesn't lose its effect. So I don't have to like have it directly before the attack. It can be like separated by a lot of random tokens, and I show this in the paper. That, like it kind of can be the very first token, 1,000 tokens, nothing, and then it runs. Okay, so the way I measure this is like pretty simple. I try a different length of the attack, and I try the x-axis. This is a log version of the x-axis, so it's like actually like quite a range. And then for the different colors, I give the attacker different amounts of tokens to play with, token activations to play with. And I can show that if I give it a lot of tokens to play with, which are the purple curves, it can with high probability actually win and predict a random t-token sequence I want the model to predict. And the fewer resources I give to the attacker, the harder it is for the attack to succeed. So I do these curves, and I read off kind of the threshold amounts, and I plot them like this. I plot them as, on the x-axis, the length of the attack, which is kind of like the resource for the attacker, and on the y-axis, the number of target tokens they can successfully influence. And these things are extremely linear. Like I was like so surprised to see how like great these things were. And the slope of this curve, so the theory is essentially simple. The theory is the dimension of the input determines the attacker controls, determines the dimension of the output they can determine. And so that's the slope. The constant of proportionality is the amount of tokens on the input that are needed to convert a single token on the output. And I can read off these numbers, this kappa constant here. And for this particular model here, I read the k to be 120 roughly, which means that each token's activation that I can like play with allows me to determine additively 120 tokens on the output. So give me access to a single token on the input, and I can make the model say 120 tokens exactly as I wish. Give me access to 2, I can make it like predict 240. So it's like very linear in this, and it like fits nicely with kind of the dimensionality cause for adversarial vulnerability. Yes?
So I don't mean to be skipping ahead if this is what we're going to, but does it mean that each token needs something like 80 dimensions to be specified? And you can sort of
I'll talk about it very soon. This is good question. So this turns out to be very universal across like model sizes. These graphs span models with parameter counts ranging from like tens of millions to like units of billions. So it's like a huge range of different models. And I always find this kind of like linear scaling law between them, kind of like meaning that the number of tokens an attacker controls determines linearly the number of tokens they can dictate on the output. But the slopes are different, right? But it turns out if you read of the slopes and convert the slopes into bits, and you basically, every model has a different dimensionality of the activation. One of them has like, whatever, 128, one is like 1024, another one is like, 2 to another power, typically. So each of those numbers is 16 bits. And if you do this conversion correctly, it turns out there is a very fixed number in a bit-for-bit manner, where roughly 20 bits controlled by the attacker on the input among the models I empirically studied is needed to determine a single bit on the output. So thinking about dimensions is hard because the input has floating point continuous dimensions. The output has like categorical class outputs. So, but if you kind of think about it as bit rates or kind of binarized versions, you can convert the floats into like the number of bits specifying them, and you can convert the classes into log2 of the number of classes, which is the number of bits you need to specify that token. So 50K vocab means you need roughly 16 bits to determine that, specific token. So I found this attack resistance roughly constant between models and roughly 20 bits are needed to influence a single bit on the output. This might be different between models, but surprisingly nice and regular numbers despite the 3 orders of magnitude of parameter count changes. Someone asked about tokens, right? So more natural way of attacking the model is by switching token for another token on the input. Not playing with the activations, but like only having access through the API level of access where you kind of just give it a sequence and it predicts a sequence. I did this and I exhaustively per axis, but greedily, between axes, swept over numbers of attack tokens by just like replacing one for another, trying all the possible combinations for each token, all the possible vocab choices, fixing it for the one that like maximizes the probability of the outcome I want, fixing it, moving to the next one, doing the same thing, fixing it, and repeating it multiple times. And I found that you'd roughly need 8 tokens on the input to dictate a particular token on the output as a continuation. So it's like way, way weaker, right? Like before that, a single activation could force 120 tokens on the prediction. Here, I need 8 to get a single one dictated on the output. But if you actually look at the bit rate of this, in a bit for a bit fair comparison between them, because this is a way poorer way of influencing the model, you end up getting a roughly, twice smaller kind of bit for bit comparison. So just let me repeat, despite the huge difference between the attack methods here involved, the amount of influence each bit on the input exerts on the output of the model is roughly only within a factor of like 2 between each other. So it's very regular. The actual strength is like 1,000-fold different, but if you do it fairly in this dimensionality-aware comparison, they're roughly equal ways of influencing the output of the model. So to me, this is very encouraging. And I think I'll leave it for the end. This is like the very last thing. But basically, in the end, I thought, well, the theory I'm kind of like a proponent of is that the number of input dimensions and the number of output dimensions are the relevant numbers for the existence of adversarial attacks. In particular, if the number of output dimensions is lower than the number of input dimensions, then they exist. Otherwise, they don't exist, right? So I actually plot all the attacks I make on this like 2D grid, where on the x-axis I've got the input space dimension, on the y-axis I've got the output space dimension, and so these would be like literally impossible. This is the line I told you about, and I do not find any single attack that succeeded in the regime where the output is higher dimensional than the input. So fair enough, this is expected. These are possible in principle, but I find this kind of like constant of 20 converting kind of bits on the input to the bits on the output. And so, it's like not exactly the one-to-one that like is the theoretical limit according to me, but like it seems to be at least linear, and like it's like a constant kind of slope in this space under which it seems attacks are possible. So if you kind of color in all the experiments I ever did, they end up like nicely lining up in this triangle where you kind of like need 20 dimensions for each dimension on the output you would like to dictate. And if you actually add the token activation, the token attacks on this, they also lie in the left bottom corner of this triangle. And a similar thing works for vision models and vision classifiers as well, not only for language models. So to me, this graph is like a nice kind of like leading evidence that the dimensionality aspect of the situation is a key thing for determining whether adversarial attacks are possible or not. And therefore, this could guide us towards potential solutions where we kind of limit the input dimensionality or kind of maximize the output dimensionality. All right. So this kind of provides like a unified resource theory or model for AI security in a way, but it's a baby first step towards it. But I'm trying to build it up right now. All right, thank you very much. I'm glad I could tell you about all these things that I really care about. And if you're interested, get in touch. I haven't really opened the swap card or Slack, so it's better to kind of catch me physically in the building if you want to talk to me. And DMs on Twitter or X work really well, and my email is also open. Thanks a lot. Yes?
So we have time for questions. We have 20 minutes, so it's like for
nice.
a lot of discussion.
Hi. So in the beginning you mentioned that it was surprising that such small deviations would be attack vectors, and I come from complex systems, and to me it wasn't. But the interesting part, though, where I want to ask whether there is an approach to explaining this, is how a static attack works on all or
So you're asking like if the fact that like a single attack can convert multiple images into a dog means that like the relevant area for image one is like this patch, and like a relevant area for another image is like another patch. I don't know, and I don't think it's known. I think like I'm not like 100% familiar with the literature, but this actually would be a really nice thing to study, the localization of the influence. I suspect it's not this simple. I suspect it's like the full thing, somehow like adding its effect. But yeah, I'm not aware of any kind of like pre-existing result that answers this. But I'm curious actually, why is this not surprising to you? Because the surprising thing to me is that these things can withstand like huge amounts of influence. It's just these very particular influences are like extremely damaging even at like weak strength. So if they were brittle overall, this would not be surprising. If I could just like add a little bit of noise and they would be completely broken, I would not be surprised. But given the amount of robustness they have, then in the light of that, like it's surprising to me. I mean, not anymore, I got used to it, but why was it not surprising to you? And also, was it not surprising before they existed? Like, did you actually like predict it?
Wouldn't have predicted it because I didn't think of it, but
Yeah.
complex systems is kind of their property, that they're very dependent on input data, and there are areas where they're robust, like weather systems, for example. If you change the temperature and humidity in a certain area, it's not a problem, but then you change the last digit of humidity in a certain area and they completely go off the rails. That's just a known phenomenon.
I think Hansa.
So I don't think this intuition from complex systems actually carries over. Like if like you have like sensitive dependence on initial conditions, but you kind of end up in like very different spaces. So this is robust. Don't try to explain, like this is like robust noise. You take like a perturbation in a random direction and you kind of like fall in the same basin. So this is like pretty different, but if you like you can kind of with a lot of control, you just need to I don't know, like push the system in a very particular direction, and then you can like specify where it ends. So I don't think there's like some like very clear like analog in complex systems for that.
That's with completely differentiable systems. There are also systems with non-differentiabilities, and they behave exactly that way.
Thank you. I guess we could open a discussion circle later. I'm still surprised, by the way. I'm not unsurprised. Also, given that humans don't seem to have them. It's like, to me, the transfer between these models of the same attacks and their kind of like shared vulnerability, not being shared by the human that I assume, or like many people assume, is like exposed to the same data, works in a similar way, that's surprising. And I'm talking about more about that in the follow-up paper next week, but yeah.
Yeah, I have a question on the robustness. So when you showed these adversarial attacks on animals and these things and suddenly recognized it as a different thing. Now, if you ask AI scientists from different fields, they say, oh, look, this is trivial because we humans, when we see a picture of a dog, we have also the association to it, like, how does the dog feel like? How is it, for example, to cuddle with it? How does it smell? What kind of noises does it make? How does it influence the environment? All this sensory input which we have as a background in us, which we quite grown up. And often the answer is like, okay, it's an easy fix to like just give access to model to like this sensory input, which is apparently very important. And now I'm a theoretical physicist, I have no idea on how this might work or not, but it seems like at least the intuition-wise seems very reasonable that the AI does not have an idea on what a dog is or what these things is. So what would be your response on such a...
So just to rephrase you, I think you're saying the key is like multimodality, right? Like you don't see just the picture of a dog, you see the olfactory, whatever input, you see the feel of the fur and whatever. Like, you know, obviously we don't have a model that's like as multimodal as a human, but we have multimodal models. Like CLIP is a multimodal model. It's got like text input and the understanding of text and also the image input and the understanding of images. And these things are also fooled. So despite the model having a much richer understanding of what a dog is, and all the like textual associations that like dogs bark and dogs whatever live in a doghouse, and like all these things that like an image model might not have, it just sees groups of pixels, so it like has no idea about the other associations. A vision language model, that's like the typical thing, GPT-4, Gemini, these things do have at least another modality, which is text and image, and yet they suffer from the same vulnerability. So if the remedy certainly isn't just like simply adding more modalities and adding more associations to the model.
Yeah, the argument is more to add strong modularities, because like the amount of information which we receive by experimenting and by touching something is far more than from visual and text.
But I might, if you show me just pixels of a dog, I can still recognize a dog, right? I don't need the fur, the feel of the fur, and the smell of the dog, and like the.
Yeah, but you have an idea of what a dog is, because you grew up, say, 20 years surrounded by many, many different things.
So you're saying like the training procedure is kind of different, even though that I can. I agree. Yes, I agree.
Now because you have all this big prior, you are able to distinguish one picture from the other. But assuming you would have just grew up without the possibility to touch anything, then it might be different.
I think that this is like plausible, but I haven't seen convincing evidence this is the case. But this sounds plausible to me, that this plausibly might be the solution. And so just like as a side note, I think it's very likely that humans actually do not have adversarial attacks of this sort. I think in the kind of like AGI lore around less wrong and stuff, it's often kind of assumed like, the super intelligence, like machine god will like come to you and like blink this like diode at you at just the right pattern to like make you think thoughts and whatever, like, or like just like destroy your nervous system and stuff. I imagine like if the diode is like really strong, it like burns like a hole into your like actual biological brain, then it could do that. But I do not assume like these kind of like weak, like specific patterns that like destroy you are a feature of the human visual system. I actually do not think that humans like likely have attacks of this sort. So whatever we do, I think there is something that causes us, I think, so this is all my speculation, not to have these and to cause the machines to have them. That's whatever the procedure is used for training them and like how to use them. So I think, yeah, I broadly agree with you, but I haven't seen kind of convincing like body of empirical evidence for that.
Okay, thank you very much.
Who wants next? Yeah, so you mentioned earlier that the quantized model are more difficult to attack.
Yes.
Why is that?
Oh, it's just harder to like do gradients when the numbers are like stuck at, just like the gradient computation is harder, but it's not, if the activation is quantized, you can like move to as many points, like I have a picture that I would like to, right, like I can choose like the 2 to the number of bits times the number of dimensions values for the activation vector. If it's quantized to like a lower number of bits, there's like fewer things I can choose from. So just because of that, it's kind of harder to find the thing that's convincingly something. So it's like a simple kind of like counting argument. The higher the dimensionality, the lower the granularity of the more kind of finely defined the number is, the more things I can choose from. So I think that's the simple argument for. Also, there's like a practical notion of like the gradient, like is harder to compute.
Yeah, and just another question. So, do you think that in general the quantization could affect the safety more than performance?
Oh, I'm not sure. I don't know. Sorry.
Thanks for the talk. It was super interesting. I have 2 questions. May or may not be related. The first one is like, can you speculate on like what is going on here? Why would adversarial examples generalize across different models and so on? It's like, why is there something kind of feature-like or what's going on?
Yeah, actually, we've been looking at this with Václav over there over like the last few months. I don't know. There's a pretty famous paper called Adversarial Attacks Are Features, Not Bugs by Alexander Maudry from MIT. I'm like partially convinced and partially unconvinced by the paper. I think what they basically argue that there are like genuinely predictive features in the training set that do generalize to the test set, like pixel configurations are genuinely predictive of a dog, of a cat, and they're easy to recognize for the model, they're easy to learn for the model, but they're easy to break by small perturbations. Like this is just like rephrasing of what's going on, but they say the transfer is a genuine feature of the model detecting correctly like generalizable underlying features in the training set. So they show, this is like a sad story, so just at the beginning of COVID, I went for a run and I thought, oh, it would be like crazy if I took like these adversarially attacked images and I labeled them as the target class. So I would take a tree, turn it into a dog, which still looks like a tree to a human, but it's like a dog to the machine. I labeled it as a dog. I train a new model on this. I wonder whether it would generalize to the actual unperturbed images, right? It turns out to be like a key experiment of this like famous paper that I didn't know about. But essentially, if you take images and attack them to look like something to a machine learning model, and take a fresh model from scratch and train only on these perturbed images with the incorrect labels, the labels that are the target labels for the attack, the model learns a generalizable like classification function and works on the unperturbed test set. So despite never seeing anything that looks like a tree, labeled as a tree in the data set, not seeing anything that looks like a dog, labeled as a dog in the data set, you can convey the same information to the model and that it works and generalizes correctly. Do you have a thing to add here? Oh, sorry, yeah. Yeah, so I kind of got lost in this, but that paper basically argues this is a feature, not a bug. It's like genuinely detecting these very brittle but predictive features in the underlying data set. They are shared between the train set and test set. That's why the model actually like generalizes correctly. And one way I speculate to remedy this is to discourage learning of these kind of like brittle features, because obviously it has robust features too, right? You can look at the picture. It's got, the dog has ears and the turtle has a shell. These are like recognizable, robust features to a human. It just seems that the training procedure, the architecture, whatever is going on, in aggregate causes the model to overfocus on the brittle features. They're also predictive, so that's why it works. But yeah, that's the story, kind of the most accepted story right now.
And the question too is like, at the start you said adversarial examples as like A/B alignment, and that this you see this as like a key step to alignment. Wondering if you could motivate that claim a bit more.
Yeah, my claim is basically if you cannot align the implicit function, even in this very specific like domain that is very controlled, very poor compared to like the actual AGI alignment, we have no chance of aligning the full thing. Like this is a very like constrained, concrete version of the problem. I have an implicit function. I'm trying to communicate the function to the machine. The machine learns a function that like seems to be roughly the same and yet catastrophically different in like a regime in which I probe for the differences. So to me, the fact that like so far we haven't really resolved this in a satisfactory manner shows that like at least our techniques are like for sure too weak for the like the actual like broad problem that we're trying to attack, because we cannot even like align these like implicit functions in our heads and the explicit functions in the neural networks that we're trying to learn. So in that sense, I view this as like alignment. Here, I mean like the literal alignment between the function I have in my head, you have in your head, and the thing conveyed to the machine. But you know, it's like the analogy might be strained, but to me, it seems like pretty clear that solving this is easier than solving the AGI alignment problem.
Maybe you have in the alignment space like noticed ideas like the natural abstraction hypothesis, for example. The idea that like all types of systems, they all kind of like arrive at like similar concepts and so on. So I think like this actually provides some like empirical evidence on the hypothesis. Like what you've just heard, like you can kind of like, if you think about it for a while, it kind of like tells you something like you have a net. It like learns what a tree is based on images. Empirically, it seemed it didn't learn the same thing as humans. My guess is because it's like differently bounded directional, but it's actually connected to a bunch of like deep alignment problems too.
Thank you. Yeah, this is a good, to me, counterexample of the natural abstraction thing. My abstractions are obviously different than whatever the network learned, but they agree in almost every case. So this is a point against static evals, because a static eval would not see a difference between what I see and what the machine sees. I need this like targeted, motivated attacker, like a red teamer, that like tries to suss out the difference between my model and the model in the machine. So I think this is a point of evidence speaking for kind of active, exploitative evaluation of these models that are trying to like actually get to the most different or like most like unmatching point between the implicit function or the desired behavior and the behavior of the system. Because you would like not stumble upon an adversarial attack easily by just like randomly sampling Gaussian noise, right? Like you could like sample a lot. These are extremely rare. There's like another aspect of my research before. I spent a lot of time thinking about lost landscapes of neural networks, kind of the space of weights filled in by the scalar value of the loss the network has at these weight configurations. And these spaces are similarly complex. They're actually higher dimensional than these input spaces, so they're even more complex. And similarly to how you need gradient descent to find a working neural network configuration on some data set, and you couldn't sample this using random perturbations. Similar to this situation, you kind of need this like directed search to like vastly speed up your like vastly increase your chance of stumbling upon like a mismatch between the human model and the learned model. So I think this is a point of evidence for me speaking for like active dynamic evals rather than like static data sets or static comparisons. Yes?
Mike, is there?
Oh, sorry, yeah.
Thanks for the great talk. So I was wondering, how do we explain adversarial attacks from a mechanistic interpretability point of view? So if we mainly look for images because they may be easy to explain, I understood that mechanistic interpretability like is this form of building blocks, for example, like edge detector of that look on the edges and then later are composed in these circuits to more complex features. So where in this does this break?
That's a really good question. I've got an answer to that in the follow-up paper. I'm sorry, I was hoping to have it done for this talk, but I got stuck in like a review hell. So yeah, this is like a tremendous question, but yeah, I cannot answer. Sorry, but I know the answer.
Yeah, so watch Tanda's Twitter, I guess, and like eagerly like next week, like you will understand like way more. You have time for like last one question maybe.
I think
let us and we'll eager for the break so the discussion can.
I think the area there is kind of like under asked.
So I just a question like, is this adversarial avoidable if you have the access to the model with an activation? Like I feel like it's kind of a argument for if you take the architecture and the language model as a whole neural network, it kind of shows that it can just learn everything, right? It can just, you give any target, it can just learn it. And I feel like the way to avoid is just to seal the model to avoid any access to the weights. I feel like the same for human brain, right? If you just have a you have access to the activation and how find a way to shrink by like a gradient descent, our brain can also be attacked, right?
But the problem is the transfer of these attacks works. So you don't have to give me access to your model. I can get access to any model, and then I design it against that, and then I give it to your model that I never saw in detail, and it still works. It doesn't work as well, but like it's still, I don't have to have access to your particular weights. It's enough to have access to a proxy model that's cheaper, smaller, open source.
This actually is the difference between the analog network and the machine network, which is like the binary digital network, so they can transfer how easy for human brain.
Makes sense. Yeah. Thanks. Maybe the last one. Oh, okay. Well.
Maybe last one.
Okay.
Yeah, quick question. So if you compute the distance cosine similarity between the images with the adversarial attacks and the original class, like let's say you changed it into a car, and you compute the distance between the actual genuine car image versus the attack. Do you find that the distance between these two is also small in comparison
yeah, way closer, right? You can look at the images, so you see they're similar. So the cosine distance between the pixels will be roughly, how pixel different the image is. So given that I can like perturb it with like 8 out of 255 L infinity norm maximum change of the perturbation or whatever, I can bound it to be a very small thing, and yet it works. The standard attack size people like work with is 8 out of 255 L infinity. So like each pixel can be at most shifted by 8 up or 8 down in each color out of 255 values, and they look nothing, like actual like substantial modifications to the image. So the cosine vector between the pixel array of the original and the modified image are basically the same. They're like is cosine of 1 essentially, and yet the response is like completely different. So that's kind of the key. Like it's an outrageously disproportionate response to a small perturbation on the input.
Right. So like in summary, the car and the truck have a certain distance, and then when you attack the truck, that's now masquerading as a car is way closer.
That's right. Yeah.
Even though to us they look nothing.
That's right. Yeah. So the adversarially attacked car into a turtle, you wouldn't be able to find a turtle as close to it in the training set as you kind of generated by attacking the original image. Yeah.
And sorry, quick follow-up. If you perturb the attack with like the kinds of noise that these models are robust to, it still works then?
Yes.
Okay.
Yeah. Thank you. Thank you.